Hello and good evening, everyone. Hope I am audible to you. Can anyone please confirm that whether I am audible? You can put in a message in the chat if I am audible. Okay, thank you. So, good evening, all. Thank you for joining today. Welcome you all to the problem solving session of the course Transmission Lines and Electromagnetic Waves. So, first of all, I would like to introduce myself. I am Susan. I'm a teaching assistant of the course. Uh, Basically, I'll be dealing the problem solving sessions every week, especially the assigned day is for me is Saturday from 5 p.m. to 7 p.m. So basically, let me start with my introduction. So, I'm a PhD scholar at Department of Electrical Engineering at IIT Madras. So, this problem solving session is aiming at clarifying your doubts uh, based on the content of the previous week, which will eventually help you in solving some sample problems or figuring out how to do the assignment questions. But definitely, we won't be discussing any of the assignment questions because that is for you to test your understanding of the course. So this session meeting link is will be shared with all of you in the NPTEL site, and you will also have a reminder every week about the session. Uh, so, today's session, I would like to include the content of week 1 and week 2. And so, as you all know, the course has already started from 23rd Jan. And the content of, in fact, 3 weeks have been uploaded in the site. So, hope you have already started going through the video lectures. And I think the first and the second assignment is due on coming Wednesday. So probably you might have gone through most of the lectures of from week 1 and 2. So let us go into some of the sample problems based on the content of week 1 and 2. So to start with, let me just give an intro on the course. So this course is Transmission Lines and Electromagnetic Waves, and the instructor is Professor Anantha Krishnan. And the books and references given in the NPTEL site is R.K. Shevgankar, Electromagnetic Waves. So this would be the basic reference. And to say something about the course in general, it's giving an overview of practical aspects of engineering electromagnetics. So, and to some extent, I mean, or to a great extent, the programming and how to visualize really the electromagnetics and transmission lines. So, before going into the session as such, so let me just give you a simple um, poll question. All of you can try answering to this poll. So this is a general poll question. You can try to um, learn how to use the poll. So down right activities you can see. There you find this poll. You can access the poll. You can choose your option. So the first, just a question to ask you all. As an NPTEL learner, which of these category do you belong to? So please do access the poll and give an answer for the question. So hope you can find where the poll is. So that is in the Meet window, down right corner, you have activities in the shape of a triangle, square, and a circle. There you can find the polls. Yeah, I think I got one person's vote for the poll. All of you can try to access the poll. This will be very nice if you could access this, because later later on we will try to incorporate this in uh, even for the MCQs while discussing the sample problems. It will be helpful if you could try to access the poll and give your answer. So basically, I think I got a few votes. Many might be trying to access the poll. So please do try to access the poll and learn how to uh, use the option of polls. So, so let me carry on towards the our discussion on week one. So, so this week, let me start with week one, which covers lectures 1 to 3 and the basic concept takeaway ideas from the lectures 1 to 3. So, the first discussion starts with the delay, notion of delay in the interconnects, and discussion on transit time. So as you all know, you as if you have already gone to the video lectures, transit time, maybe if you denote it by tau, is can be defined like length of a transmission line divided by velocity of the velocity of the signal. So this gives us the transit time in traveling from one point to the other point on a transmission line. So where L is the length of the transmission line and V is the speed of the signal. Then we come across this low frequency circuit analysis and high frequency circuit analysis uh, in the in the lecture videos. So as you already know, the high frequency when we go for higher and higher frequencies, we need to consider a section of transmission line, and then we can apply the low frequency circuit analysis. So hopefully you remember from the lecture videos the circuit model of a transmission line. So I'll just quickly refresh the concepts. So basically these are the primary constants of a transmission line, where R is the resistance, L is the inductance, G is the conductance, and C is the capacitance. So in case of a lossless transmission line, so as the lecture videos go on, you understand that when you say lossless transmission line, what is the condition? Where R is equal to G, R and G is 0, where there is no resistance, where there is no conductance. So basically, there is no losses. So R is going to represent a resistance, and G is representing a basically a leakage current, so which is not present. So ideally the transmission line model becomes LC. So an ideal lossless transmission line model. So, so this is where we start with in the lecture videos, starting with the lossless transmission line and going on with the telegrapher's equation, derivation of telegrapher's equation, and then towards the wave equation and the solution. So I'm not going to go into the detail of any of the derivations. So let us discuss only the takeaways. So first is about the wave equation. So to talk about wave equation, the solution of wave equation. So as you all have seen, the solution of wave equation consists of two terms, basically a forward wave and a backward wave. So I can say the forward traveling wave and the backward traveling wave. So the concept of backward traveling wave. So if you take a transmission line with some load, and there is your source. So if you have a transmission line, the solution for your wave equation consists of a forward wave and a backward wave. So this backward wave becomes relevant at certain conditions. So hope you have understood those things from the lectures. So backward wave will exist only if it's a finite length transmission line, and also uh, there is there is an complete impedance. Say for example, uh, this is the impedance of the transmission line, that is Z0, and say this ZL is the load impedance connected to the transmission line. For So if at all Z0 is not equal to ZL, then we say that the impedance is not matched. So there will be reflections back, and that is your backward wave. So your backward wave does not exist if the impedance is perfectly matched, or in other way we say that the maximum power is transferred to the load in that kind of a impedance matched condition. So that's all to brief about the forward and backward traveling wave. Now to discuss about the characteristic resistance. So that is a concept which has been discussed. So characteristic resistance of a lossless transmission line is given as root of L by C. So that is so in case of a transmission line, we say that it is root of L by C. In case of a material, say for any material, we say it in terms of eta, which is basically root of mu by epsilon. So all of you know what is this. So the permeability and the permittivity. So basically L and C is connected to the mu and epsilon. So so that's all about some of the basics of the lossless transmission line. And then the next topic of discussion was on, especially on finite difference method. So there you have come across the basics of finite difference method. Basically the different types of differencing, that is forward, backward and central differencing. And so the different equations for the different differencing methods, and also the second order partial differential equation. So in second order partial differential equation and how to solve it with the help of a finite difference method, and we come across solving Laplace equation, and also solving wave equation and telegrapher's equation. So all these had been discussed in the lecture videos. So let us come to these in detail while we solve some of the sample questions. So let us go on to some topics which were discussed in the later. So one is voltage and current waves, then reflection coefficient in case of open circuit or short circuit or matched load, and then we come across the time domain reflectometry, which is helping us in which helps us to analyze the fault in a transmission line. So we'll discuss a sample problem on this also. And towards the end of this week one, we also have the voltage bounce diagram. So let us try to solve some sample problems. So I have a few questions with me which are displayed. So you can all try to solve the question, and definitely we can use the chat window to discuss the answers. So the first question is: a 1,000 kilometer long 50 hertz power transmission line has a signal speed of 2 into 10 power 8 meter per second. What is the transit time? So the first question is on transit time, and the second question for the same question, the second part is wavelength of the AC waveform, and the third question is phase difference between the two ends of the transmission line. So let us start by writing down what are the information given to us. The first is the length of the transmission line is 1,000 kilometer, and the frequency is 50 hertz, and the signal speed is 2 into 10 power 8 meter per second. So I request you all try to solve the question along with me and try to give the answers in the chat. So let us start with transit time. Transit time is nothing but length of the transmission line by velocity of signal or the signal speed. So length is 1,000 kilometer. So 1,000 into 10 power 3 by v velocity is 2 into 10 power 8. So I expect some answers in the chat. I think these are the very first question is a very simple question. So try to give in the answers in milliseconds. You can all try. It's very simple. Yes, I think someone has answered. Yeah. A few answers have come. I'm seeing the chat. Okay. So yeah, most of you are very close to uh, this. Okay. So this is a very simple question. So the answer is 5 milliseconds. So now let's see the second part. Again, this is very simple. The wavelength. How do we calculate the wavelength? Very basic equation. All of you can try. Very basic equation. Lambda is equal to V by F. V is the speed, signal speed, and F is the frequency. Can you please try? So please do try and try to give the answers in the chat. Mm, can you recalculate? Whoever has given the answer, can you please recalculate? So basically velocity or speed is 2 into 10 power 8 and F frequency is 50 hertz. Can you please try again? Yes. So we got an answer from Dr. J. Sujita. Thank you. 4 into 10 power 6. Okay. So let's see. So to answer this question, so in kilometers, it is 4,000 kilometers. Okay. So let's go ahead to the third part. In the third part, phase difference between the two ends of the transmission line. Phase difference between the two ends of the transmission line. So to find out this, we need to see that beta is equal to 2 pi by lambda. 2 pi by lambda. So all of you know what is beta. Uh, that is the phase constant, which is in radian per meters. So we can say how many radians per meter. So when you calculate this 2 pi by lambda, what do you get? 2 pi by 4 into 10 power 6. Can you find this beta? So beta is giving us an idea of what is the phase difference per unit meter. Yeah, right answer, Dr. Sujita. So the answer is 1.57 into 10 power minus 6 radian per meter. Okay. So this is the phase per meters. Now, can we calculate the phase difference? So when we say a transmission line like this, so it has, say, first the beginning end and the beginning and the end. So AB is the start of the transmission line and CD is the end of the transmission line. So the length of the transmission line is something which we already know. And we also know that per meter how much is the phase or phase. So can we calculate from this what is the phase between AB and CD? Because we already know the length of the transmission line. So we just have to multiply it by this beta which we have already got. So can you calculate this and let me know what is the phase difference? I request everyone to try calculating the phase. So we already know the phase constant beta, and we also know the length of the transmission line. So how much is the phase? So the length of the transmission line is 10 power 6 into phase is 1.57 into 10 power minus 6. So the final answer would be 1.57 radian. 1.57 radian. So if there is a confusion between the unit, if there is a confusion regarding the units, always remember the phase constant is in radian per meters. So therefore, the phase which we calculate is in radian, and we can convert it to degree. So 1.57 in radian. Can you tell me the options among the four options? Can you give me an answer? 1.57 radian. So please do try options A, B, C or D. Please do type in your chat. All of you can try. So basically it is 1.57 radian. So is it pi by 4? Is it pi by 2? Or is it pi? Yes. So answer is right. It's 90 degree, or we can say pi by 2 radian. Pi by 2 radian or 90 degree. Yes. So I hope this question is clear. Actually, this is a very simple question. So if there are any doubts, please do ask. If there are no doubts, I'll go ahead to the next question. So coming to this question, a transmission line of characteristic resistance 50 ohm is loaded with a load impedance ZL, which is RL plus JXL. Magnitude of the reflection coefficient at the load is measured to be 0.6. If the real part of the load impedance is RL is 50, find the number of possible values for imaginary part XL of the load impedance. So let's say we have a transmission line with a characteristic resistance RC, that is 50 ohm, and you have a load connected, and this load is being represented as ZL, which is RL plus JXL. Now, the magnitude of reflection coefficient at the load. Okay. So, gamma L, reflection coefficient at the load. So, why would a reflection happen? Because the characteristic resistance is not same as the load impedance. Definitely there will be a reflection. So that reflection coefficient can be calculated with this equation ZL minus RC by ZL plus RC. So this is gamma L. So the magnitude of that gamma L, that is modulus of gamma L, is measured as 0.6. If the real part of the load impedance, that means RL. So we already know what is RL, that is 50 ohm. Now how many possible XLs are there? Okay, and let us also calculate XL. So uh, so let's see, when I say modulus of or magnitude of the reflection coefficient is 0.6, so this gamma L could be plus 0.6 or it could be minus 0.6. So here lies the clue. So gamma L could be plus 0.6, that is with phase 0, and or it could be minus 0.6, that means it is with the phase of 180 degree. So that is the phase, that is indicating the phase of the reflection coefficient. So this gamma L, I need to substitute it here. So if you can substitute this gamma L and also knowing this RL, and we also know the RC. So from that you can also calculate XL. So can you all try this question? I have given a few hints and clues. Can you all try for a while? So I can give a starting point. ZL is RL, that is 50 plus JXL minus RC is 50 divided by ZL plus RC. So when I say ZL plus RC, 50 plus JXL plus 50, which is nothing but gamma L. So this could be simplified as JXL by 100 plus JXL. So this is gamma L. Now when we take the magnitude of gamma L, what we have is XL divided by square root of 100 square plus XL square. And this magnitude is 0.6. Now, will you be able to calculate XL? Can you all try this, please? To simplify this, XL square by 100 square plus XL square is equal to, the squaring both sides, so this becomes 0.36. So I think now it's a straightforward question how to find XL. Uh, any answers for the value of XL? Hopefully you can say how many XLs will be there. I mean, what is the number of possible values of XL? So the value of XL could be plus or minus 75. That is, there are two possible values for XL, or the imaginary part of the load impedance. So basically, the load could be RL plus or minus JXL. So that is 50 plus or minus J75. In in both the conditions, when the load is 50 plus J75 and 50 minus J75, you have the magnitude of reflection coefficient to be 0.6, or in other words we can say reflection is 60% reflection. So I hope this question is clear to all of you. Any doubts you can ask in the chat. I can wait for quite some few um, minutes. If you have any questions, please do ask. Okay, so I think I can move on to the next question. So this question, the question is, a two-conductor lossless transmission line of length 1 kilometer and a total line capacitance of 50 nanofarad is connected to a 1 volt source at t is equal to 0, and the signal was received at the end of the other end of the line at t is equal to 5 microseconds. Velocity of the signal on this transmission line. So to start with, the length of the transmission line is 1000 meters or 1 kilometer, and the line capacitance connected to the source is 50 nanofarad. So, and it is mentioned that it is connected to a 1 volt source at t is equal to 0, and the signal was received at the other end. So that means from one end of the transmission line to the other end of the transmission line, it takes 5 microseconds. So for the signal to reach one end of the transmission line to the to the other end of the transmission line, it takes 5 microseconds. So we know that the transit time is 5 microseconds. Now, will you be able to calculate the velocity of the signal on the transmission line? So you know that transit time is length by velocity of signal. So you can easily calculate the velocity. velocity is length by tau. So length is 1000 divided by tau is 5 microseconds, 5 into 10 power minus 6. Can you give an answer for the velocity? So it will be 200 into 10 power 6 meter per second. Now going to the second part. So the capacitor or capacitance C. So basically C capacitance is per meter. So how do we calculate that? We already know the total line capacitance. So say for example you have a long transmission line of length of 1 kilometer. So the total capacitance of this transmission line is 50 nanofarad. Okay. So out of that you want it for 1 meter how much it is. So that is very simple to understand. That is 50 nanofarad divided by 1000 meters. Give me the answer. So that will be the capacitance per unit length. So that will be 0.05 nanofarad per meter. But if you notice, this is in picofarad. So always do remember the units. Try to notice the units. So if you want to make it in picofarad per meter, you have to make it 50 picofarad per meter. I think someone has responded in rightly in the chat. Yes, that is 50 picofarad per meter. Thank you, Anandan, for responding. Thank you all for responding. I think many answers have come. All of you keep trying. Yeah. So now we know the capacitance and we also know the velocity. So once if you know velocity and capacitance, can you calculate L, that is inductance? So we know that velocity is 1 by root LC. Okay. From this we can calculate what is L. It's very simple. Can you all try this quickly? Can we have the answers for inductance? So the velocity is 2 into 10 power 8 meter per second. Okay, some answer has come. Mm, can you try once again? I think somewhere some mistake has happened. Maybe it's with the units. Maybe it's just a simple mistake. You can try once again. So please do remember, don't take this 50 nanofarad. You have to take this. Okay, some answer has come. I think it is close to. Is there a point 0.5? I think missed to mention a decimal, I think. So the answer is 0.5 microhenry per meter. And so once you know L and C, you can always calculate RC, or the characteristic impedance or characteristic resistance of the line, that is given by root of L by C. So what will be the answer for RC, or the characteristic impedance? Very simple, it's 100 ohm. So that will be the characteristic impedance of the transmission line. I hope this question is clear to all of you. We'll just move on to the next question. Okay, so let's discuss this question. So as you can see in the figure above, the voltage signal, say, please note it down. The voltage signal is traveling from the center of the line A. So this is a transmission line. So you see, from here to here you have a transmission line. Basically you have a transmission line. Okay, the center of the transmission line is A. Okay, and the voltage wave, okay, there is, if you see the time, so this axis is time, and this axis is the length of the transmission line. You can notice that at initial time there is no signal, and at some time there is a signal at the center. Okay, signal at the center, and it is propagating in both directions, like in forward and in backward. So as the time go on increasing, so this wave is propagating backward and this wave is propagating forward. So this is basically a voltage wave. So as given in the question, so voltage signal is traveling from the center of the line towards the edges of the line. So what are the edges? One edge is B and the other edge is C. Okay, with increasing time. After the first reflection from B and C. Okay, so there is a reflection at the boundary. Say when I say boundary, boundary is nothing but the edges. One edge is B and the other edge is C. So these two are acting like a boundary. So once the boundary is hit, the reflection starts occurring. So now choose the correct voltage and current waveform. So let us find out what is the correct voltage and current after the first reflection. So first reflection happens from B and also from C. And there is an information given to us. What is the information? The end B is short circuited and the end C is open circuited. So C, end B is a short circuit and end C is an open circuit. So this is a very crucial information given to us. So what will happen to the voltage waveform? What will happen to the voltage waveform at a short circuit boundary and at an open circuit boundary? So can we draw a voltage waveform once immediately after the reflection? I mean, immediately after the reflection, what happens to the voltage wave? So let's try to analyze this question. So you have a voltage wave. Okay. So this is the forward wave and this is the backward wave. So this is basically a voltage signal. Okay. So now here you have a boundary B which is short circuit and here you have a boundary which is open circuit. Now after the reflection from this boundary and this boundary, what happens to the voltage wave? So the question, I hope the question is clear to all of you. So now we need to understand what happens at the short circuit boundary. So at a short circuit boundary, all of you know what is the gamma L, that is the reflection coefficient. So let's start from the basic, very basic, ZL minus Z0 by ZL plus Z0. Okay, that is the basic equation of a reflection coefficient. So when there is a short circuit, ZL is 0 and gamma L is equal to minus 1. Okay. So that means in case of short circuit, gamma L is minus 1 and also in case of open circuit. So when I say open circuit, ZL is infinity. So you all know that I don't have to derive it again. So the gamma L is equal to 1. Okay. Now given these conditions, let's see how to draw the voltage waveform. So at the short circuit boundary, there is a phase difference, that is there is a minus 1. So there is a phase difference, the voltage wave will flip. So what will happen to the voltage wave? It flips and it becomes like this. Okay. Now at the open circuit boundary, that means here at the open circuit boundary, gamma L is 1. There is no flip. Gamma L is 1, there is no phase difference. So there is no flip. So the backward wave which traveled like this will come back as such. Okay. So this is the voltage signal after reflection. After reflection from the boundary B and boundary C. This is the voltage signal after reflection. This is before reflection. I hope this idea is clear. Any doubts you can ask in the chat, or you can ask. If there is any clarity needed, you can ask. Can I have some responses in the chat, whether you understood this or not? Yes. Okay. Thank you. Thank you for the response. So I believe I am. We can go ahead. So let's move on to another question. Okay. So let's say. Okay. This will be a nice practice question. Uh, you see, the parameters of a certain transmission line operating at 600 milliradian per second. So, if you notice, the frequency is given in terms of radian per second. So, 600, sorry, not milli, mega radian per second. And the inductance is zero point 0.4 microhenry per meter. Capacitance is 40 picofarad per meter. G is the conductance, that is 80 millisiemens per meter, and R is 20 ohm per meter. The attenuation and phase constants of the line are. So we basically need to find attenuation constant alpha and also beta, phase constant. And there is another question, that is the characteristic impedance of the line is. So it looks like maybe we will have a complex impedance, that is with a real and an imaginary part. So can we all try how to solve this question? So basically we need to find the alpha, beta and z naught. So here this is not a lossless transmission line. So this is R and G are present. So Z naught is square root of R plus J omega L divided by G plus J omega C. So this is omega square root of 20 plus J into 600 into 10 power 6 into L is 0.4 into 10 power minus 6 divided by G is 80 into 10 power minus 3 plus J into again omega C. So 600 into 10 power 6 into C will be 40 into 10 power minus 12. So as we have already seen before, if it is a lossless transmission line, R and G becomes 0 and our expression becomes root of L by C. This was what we have seen before. So in case of a low C transmission line, the expression becomes root of R plus j omega L by G plus j omega C. So this is how we calculate. So once you uh, simplify, you can get the answer for Z naught. So I think you can all try this and verify whether you will get this answer. So this is the answer for Z naught. Okay, so there is a question, have to convert to planar then rectangular. Yeah. So if you need that clarity, okay, yeah, I can definitely give you that. So the numerator of under square root, you have this 20 plus j so and so. So that is something like a plus jb divided by c plus jd. Okay, so under square root of z naught is equal to. So the easy way to do this is, so this is in rectangular, convert it to polar form. Okay, so this is rectangular converted to polar form. So once you convert it to polar form, you will get something like W angle X, and here this also you can convert to a polar form. So what you will get will be maybe I can say like Y angle Z. Okay. So you can you need to convert from rectangular to polar. And how do we take this? Once you divide, you can divide the magnitudes. Okay. So you can do W by Y, and the angles you need to subtract. So angle will be X minus Z. And how do we take the square root of this? Take the square root of the magnitude. Okay, so square root of W by Y. Okay, and the angle, you have to take the half of that. So angle will be X minus Z by 2. Okay, so that's how you will calculate the final Z naught in polar form. Later, from the polar, you can convert it to rectangular form. So you can get the answer for uh, real part and the imaginary part. I hope it is clear. Okay. Yes, you need to use the calculator for conversion. Yes, you are allowed to use a calculator for converting from rectangular to polar or polar to rectangular. Any conversions you can do. So I think we discussed actually the second part. Uh, okay. So now we need to discuss the first part. To discuss that first part, uh, so we need to know about. So we already discussed about Z naught. So let us discuss about the propagation constant, which is nothing but alpha plus j beta. So alpha is the attenuation constant and beta is the phase constant. So as we said, Z naught is equal to root of r plus j omega L by g plus j omega C. You can write gamma, that is the propagation constant, as root of r plus j omega L into g plus j omega C. Okay. So once you know the gamma, so basically, so you need to calculate this, and once you calculate the gamma in a rectangular form, the real part will be alpha, that is the attenuation constant, and the imaginary part will be beta, that is the phase constant. So, however, you have same procedure you have to follow. So you have two complex numbers. Multiply those two complex numbers. Take the square root of that, and then you get the gamma. So the final answer of gamma will give you the real and the imaginary part, which is nothing but the attenuation and the phase constant. Any doubts, please ask. So I'll give you the final answers, that is alpha is equal to 2.76 Napier per meter and beta is equal to 3.41 radian per meter. So once you solve this, please do try to solve and verify whether this is correct. So now you have another question on screen. Please do try. In a lossless line, so again lossless line. So the this condition is very important. When you say lossless, r and g become 0, and the phase velocity is 2.8 into 10 power 9 meter per second given in the question. If the characteristic impedance of the line is 50 ohm, that is Z0 is given to you, find the capacitance per unit length of the line. C has to be found. So you are given with options. Can you try and see whether you get any of these four options? Uh, to help you with this, uh, I think I need to give you the clue. V is equal to 1 by root LC, Z naught is equal to root of L by C. So we know both V and Z naught, but we don't know L and C. So if you multiply V and Z naught, what you will get? V into Z naught will give you 1 by C. V by Z naught will give you sorry, I was muted, I think. Uh, so the lossless transmission line, velocity is given, characteristic impedance is given, and you need to calculate the capacitance. So we know these basic equations. From these basic equations, you can calculate what is C. So V into Z naught give us 1 by C, and V by Z naught give us 1 by L. So can we calculate C? So C, the capacitance is 1 by V into Z naught. 1 by V is 2.8 into 10 power 9 into Z naught is 50. Can you find the answer from the options here? All of you can try. So the answer is expected to be in picofarad per meter. So basically, can you quickly calculate and see which among the four options? I think there is a slight mistake. Can you try once again? So the right answer is 7.14. I think there is some calculation mistake going on. Please do try once again. So I can give you the right answer, 7.14 picofarad per meter. Hope this is clear. So let's go on to another question. So I'll be sharing my screen for another set of one more question. Uh, Please wait for a while. Sorry for the delay. Hope you can see. So So we are going to discuss this question, that is the 12th question. So probably I'll highlight the question so that you know what is that we are discussing. Okay. So this question is based on digital communication system was set up between the stations A and B, situated 1 kilometer apart using a lossless. So hello everyone. So we'll discuss this question number 12, which is being highlighted here. That is, a digital communication system was set up between the stations A and B, situated 1 kilometer apart, using a lossless transmission line. The distributed line parameters of the line used were capacitance and inductance is given to you, 96 picofarad per meter, and inductance is 0.5 microhenry per meter. Due to some fault in the line, station A was not receiving the signals from station B, while station B was receiving the echo of the same amplitude but reversed polarity 1 microsecond after sending the pulse. This fault is present at a distance of how many meters from station A? Okay, so this is the question. So let's try to solve this question. So, I'll just explain the question. So we have a station A and another station B. Okay. So the distance between these two stations is 1 kilometer. So there is a communication system between these two, and that is with a lossless transmission line. So basically, this is a lossless transmission line. The distributed line parameters. So the line parameters is given to you, 96 picofarad per meter, and inductance is 0.5 microhenry per meter. So these are the parameters of this particular transmission line. So we know that because it is a lossless transmission line, R and G both are 0 because it is a lossless line. Okay. So there is some fault with the transmission line. So if there is any fault in the transmission line, uh, so there is the situation is like this. So station A is not receiving any signal from station B. Okay. So station A is not receiving any signal from B, but station B is receiving some echo. Okay. So if it is receiving some echo, that means it is sending some signal, but somehow it is receiving back its echo of the same amplitude but reversed polarity. Okay. And that is within 1 microsecond after sending the pulse. Okay. So station B is sending some pulse, but somehow it is not reaching to station A, and it is receiving a echo of the same amplitude but reverse polarity within 1 microsecond. Okay. So now the question is, where is the fault? Okay. Can you tell the location of the fault? So the question is location of the fault. Okay, where is the fault? And so the location of the fault, that is at a distance of how many meters from station A or station B. So let's see how to analyze this question. So station B is receiving echo in 1 microsecond. So we know that the transit time or the time within which the echo is received is 1 microsecond. So velocity is equal to distance by time. Say somewhere here you have a fault on the transmission line. So there is some distance d. Okay, say distance d. So let us not denote it as d. So velocity is equal to distance by time. So from here we can write distance is equal to velocity into time taken for to receive the echo. Okay. So first we need to know, we already know the time, but we need to know the velocity of the signal. So how do we find the velocity? We already have the equation for a lossless transmission line. Velocity of signal on the line will be 1 by root of L into C. Okay, this will be the first step to try. 1 by root of 0.5 into 10 power minus 6 into capacitance will be 96 into 10 power minus 12. Okay, so can you all try to calculate the velocity and give me an answer? Hope the question is clear and you are able to try this. Can you all calculate the velocity? That will be the very first step to uh, this question. So 0.5 microhenry of inductance and 96 picofarad of capacitance. So once you know the inductance and capacitance, you can calculate the, yes, right answer. Thank you for responding. So let me write down the answer, 1.44 into 10 power 8 meter per second. So this is the velocity. So now we have two parameters, that is velocity and time taken to receive the pulse. Okay. So what is the distance covered? Distance covered will be 1.44 into 10 power 8 into how many microseconds? 1 microsecond. So 10 power minus 6. So the answer will be, what is the distance traveled? Okay. So we have to remember one thing, from the station B to the fault location and back to station B. So the total distance traveled is this d. Okay. So that will be 144 meters. Okay. So that is the total distance. So now what will be the the distance from the station B to the fault location? So that will be d by 2. That is 144 by 2, which is 72 meters. Okay. So now we know that at 72 meters from station B is the fault. Okay. At 72 meters from the station B is the fault. Now what is the distance from station A is very easy to calculate. So total length of the line is 1000. So 1000 minus 72, that gives us 928 meters. So the fault location from A, this 928 meters. So this is a very interesting question based on time domain reflectometry, which is used for analyzing the fault in a transmission line. So let me write from station P, fault location. Okay, this is from station E. Any doubts? Please ask. This is a very interesting question. If you have any doubts, you please ask. Hmm, why have to take d by 2? Okay, so why did I take d by 2? So let me try to uh, say the story again, once again, just to understand. So station B is sending a signal, okay? Uh, say station A is not receiving that, okay? But somehow after 1 microsecond, this same station B is receiving the echo, okay? So somewhere you have a fault on the transmission line between A and B, okay? That is why the signal from B is not reaching A. So the time taken, say at t is equal to 0, we send a pulse, okay? And at t is equal to 1 microsecond, you receive back that pulse, okay? So this is d by 2 and this is d by 2. So the total distance traveled is d, which will happen in time 1 microsecond when the signal speed is v. So whatever distance we calculated here as d is the total to and fro distance. I mean from the station B to the fault location and then back again to the station B. So that is the total distance traveled. So the location of fault is at half of that distance. I hope it is clear. Okay, thank you. So we have some more time left. If you have any doubts from week 1 content, we can discuss that, or else I can find one or two questions. But meanwhile, I am just giving you some time if you need to uh, ask something, you can ask any particular doubts if you have. Okay, you are asking for the second and third question. Um, in fact, even I do not know which is the second and third question which I have discussed. Mm, so probably I'll upload the recording of this session. Maybe you can check with the recording. Please mute yourself, whoever has joined. I request you to mute yourself. Okay, there is a question on the book. So I would suggest the same reference which has been given by the professor. That is EM Electromagnetic Waves by Professor R.K. Shivgaonkar. So that is the best book for electromagnetic waves. So yes, I'll be providing the recording of the today's session. Uh, you can check. Okay, so there is a question. How can we calculate the speed of form, impulse wave given by this equation? Okay, so I think this is a question from assignment. I should not discuss directly. But of course, any waveform you can see the general form of a wave equation. You can from this you can notice that it is delta of omega t minus beta z. So that is a very basic form of that equation. So from that you can definitely calculate the speed. So if you know what is omega, what is beta, you can definitely calculate. So I have given a clue, but I think I should not be giving the full answer because it's an assignment question. Okay. So let us discuss another question since we have a few more minutes left. Uh, so this question is a transmission line of characteristic impedance Z naught equal to 50 ohm is loaded with a load impedance ZL equal to RL plus JXL. The magnitude of the reflection coefficient is measured to be 0.5. If the magnitude of the imaginary part of the load impedance is 25 ohms, what are the possible values for RL? So, how many possible values of RL is there? So, to discuss this question, so we know what is Z naught. And ZL, and we also know the magnitude of reflection coefficient. So gamma is ZL minus Z naught by ZL plus Z naught. So 0.5 is the magnitude, which is nothing but magnitude of, so let us take the magnitude of the other side. So ZL is RL, we don't know RL, plus JXL. So when I say JXL, so the magnitude of XL is 25. So XL could be plus 25 or minus 25. Okay. So RL plus or minus J25 minus what is Z naught? Z naught is 50 divided by RL plus or minus J25 plus 50. Okay. So this is the magnitude of the reflection coefficient. Now let us make it little more simple. How do we take the magnitude of a complex number? RL minus 50 the whole square plus 25 square divided by square root of RL plus 50 the whole square plus 25 square. So this is equated to 0.5. Now will you be able to calculate RL? Square both sides and try. Square both sides, you get it as 0.25 is equal to RL minus 50 the whole square plus 25 square is 625 divided by RL plus 50 the whole square plus 625. So from this, it's very clear how many possible values of RL. What are the possible, uh, obviously, what are the number of possible solutions? Can you type in the chat? So obviously there are two possible answers for RL because it's a quadratic equation. So I'll give you the final answers. You can verify them. 145.13 and 21.53. So basically the load could be RL plus JXL. There are two possible options for RL. So I hope this is clear. So if there are any doubts, you can ask. So there is a question on will you provide a link after the session for material? Yeah, obviously I'll provide the material which is being used today and also the recording of the session. We'll try to share it at the earliest. If there are any questions, you can ask, or we'll just wind up the session. And so we'll meet next Saturday at the same time, like from 5 to 7 p.m. Uh, so today was the first tutorial session. So we'll try to, yeah, yeah. Obviously, you have a session on Tuesday with another TA. You can definitely join that session also if you are interested. So my sessions will be on Saturday from 5 p.m. to 7 p.m. Yeah, the portions will be same because the content coverage is same. So there will be a different set of questions which will be discussed. So basically, it is from week 1 and 2. So because the assignment 1 and 2 is due on Wednesday, so we are trying to cover week 1 and 2 content in today's, I mean, the first tutorial session. So thank you all for joining. I think I can wind up the session if there are no other questions. Thank you. Thank you for joining. Meet you all next week. Bye.